Let me share my screen and we will go from there. Sharing the screen. Or anything. I'm just going to quickly check chat. Thank you. And okay, sounds good. All right. So let's continue with chapter 4, force vibrations of damped single degree of freedom system. So again, going back to the classification that we did in the first lecture, we are still in 1 degree of freedom system or single degree of freedom system. And this time we have spring and we have damping. And we added something else to it, and that's a harmonic force. All right. So you may be wondering why we are always care about harmonic force. There are many examples in vibration that they happen due to harmonic force. But first we learn everything by harmonic force, and then soon you will learn what if I have a general force. Okay, but this is the basic. So first things first, we need to start with free body diagrams. The coordinate has been set. So I disturb this system based on the coordinate that it shows. Let's say it moves to the right a little bit. Still, I have my external force that continuously is there. Let's call that one Ft, which is a function of t, and it has a magnitude F0 sine omega t. So it's a harmonic force. The damping, the opposite direction of velocity, and stiffness obviously is resisting the motion. So I'm going to have Cx dot here, and I have Kx over here. Following the coordinate, we write down the equation of motion, which here we just need the Newton. Sum of the forces must be equal to ma. It gives me mx double dot plus cx dot plus kx equal to F0 sine omega t, which is familiar. It looks like exactly the same equations that we had before. Now our goal is to solve this equation. It's a second order differential equation. And what we need to do is guess an answer. So if I look at these terms, I can see I have x double dot, I have x dot, and I have x. So I need a function that repeats itself when I'm taking the derivatives. And also I wish to get a sine omega t on the other end. So you've seen like the from the last lectures that when we deal with the harmonic one, when we deal with a differential equation when there was no harmonic force, our guess was e to the power of omega t. So for this one, we guess a solution. And that solution, we start by this guess, xt to be equal to x e to power of I omega t. Now you may be wondering why we have a complex e I omega t. The reason is if we use the Euler's formula from math, we are hoping that by replacing the ei omega t is equal to cosine omega t plus ein sine omega t. So we are hoping, since we have both the cosine and sine term, and this original equation, we may be able to solve the problem. And apparently it is true. And maybe people in the past, it wasn't just their first guess. They tried many things, but we pretend that we just guessed this one and it turned out to be a correct guess. So anyway, here, after doing lots of math, which I'm going to just skip. And if you are interested, they are all in your textbook. Just easy, boring math. You take the derivative of xt, x dot t, x double dot t, you substitute it there, and you solve everything. You will end up with xt equal to x sine omega t plus phi or phi, both are correct. I call it phi, which x is the amplitude of vibration. So amplitude, and it has a long formula. It is F0 divided by K divided by the square root of 1 minus omega n squared, the whole thing squared, plus 2 zeta omega n squared, which we know all these terms, right? We know what is omega n. We know what is zeta. We can calculate all of these terms. So we can then calculate the amplitude of vibrations. And the reason that we substitute EI omega t with this phi, because it's easier to work with numbers when they are not complex. However, in some textbook, you may see that they just show xt as x EI omega t. But if you check the Euler formula, you can substitute like cosine omega t I sine omega t as a sine omega t plus an angle phi, which this phi, we call it the phase angle. And if we do again the math, we will find out that this phase angle or this angle is tangent inverse of minus 2 zeta omega over omega n divided by 1 minus omega n squared. All right, so I emphasize on this minus here. There is a minus there. In some textbook, they may just show like this one by positive, but instead they put the negative sign here when they write the sign omega t plus phi. So rather than sine omega t plus phi, they write it sine omega t minus phi, and they remove that minus sign there. What it shows is that this xt has a lag compared with this excitation force. The excitation force is sine omega t, but the response xt is omega t minus a value, right? So it means there is a lag. It means when we apply load, our mass is going to follow that load, but with a lag, with a delay. That delay might be milliseconds, may not be able to be seen by eyes, but there is that delay second. So anyway, this is the response to this equation. So as you notice, this is the steady state response. You may ask, why don't we care about the initial conditions and the transient response? Well, the reason is because we have damping now here, C. And as we explained before, when we have damping, when there are frictions, when the system are real, the transient response are very, very short. Just maybe the first couple of seconds or maybe even less when the system start working. And we don't really care about the transient solution. Only things that we care is this amplitude. Even we don't care that much about that phase angle, but mathematically this term is there. The amplitude is something that it's important for us. How much this mass is vibrating? What is the amplitude or the magnitude of the vibration? All right, so I'm going to stop here and see if you have any question, and I'm going to check chat to see. So Mark is asking, could we also write xt x a sine omega t? Exactly, yes. We can guess with that answer. I believe your textbook solution is to write xt. So I'm just gonna, as an alternative, write what Mark said. So you start with a guess answer, which is a sine omega t plus b cosine omega t. And that's also possible. You do all the math, and after that, you will get to the like a response, which is A2, B2, I believe here sine omega t plus phi. Oops. Sorry. And my page is jumping to the next page. And then this phi is tangent minus b over a. That's also another method. Second method to solve the equation, differential equation. All right. But anyway, either the second way or the first way, we will get to this value. So this is what is important for us. The response of this system is xt, x sine omega t plus an angle phi. We can find this x and phi from this formula. All right. So just to test, if you put zeta equal to 0, let's see what you will get. Try it on your own paper. If you put zeta equal to 0, you will see the phi is 0, right? Because tangent minus 1, 0, it gives us 0. And x gives us exactly the same formula that we had before in previous chapter for a case when there was no damping. So exactly they are the same, but this time we have damping. Now let's explore this x a little bit more by plotting it, okay? So I'm gonna come here and write it down again. So then we attempt to plot it. So this time I divide x by f0 over k. And it will give me 1 minus omega over omega n squared plus 2 zeta omega over omega n squared. So that's exactly the same equation, except I move that f0 over k to this side, to the left side. So if you notice this part, the left side doesn't have any unit because x is displacement, f0 over k is displacement. We can call this f0 over k, we can call it x0, like the amplitude of vibration when there is no actually sine omega t. It is just you apply f0, this is how much it deflects. And this ratio, people call it m, magnification factor. Okay, so this m, which is exactly this one, is an important parameter for us, which we like to discuss it a little bit. All right, so let's first try to plot this one. We can use the plot on the left, but I always try to plot it myself because then I can think what's happened actually. So let's say if this is m, I'm just trying to produce the same things again here. So this is m, and over here, this is omega over omega n. So first things first, when omega over omega n is 0, obviously it gives me value of 1. So let's then draw a line at 1 and draw this line at 1 as well. These are the values that are critical for us. So this is 1 and this is 1. At the beginning, when I don't have any omega, if you substitute in the equation, m is 0. So let's just focus for the case when zeta is equal to 0. Nothing, and no damping. Zeta is equal to 0. So we have the exact same equations that we had before, right? So this goes to infinity, and this one comes back and end up at 0 for large value of omega over omega n. We notice also it crossed this line 1 at some numbers. If we substitute that number, so it gives me square root of 2. We had that one before. Now let's consider the cases when zeta is not 0. So this is for a case when zeta is equal to 0. All right. So for simplicity, let's let's call omega over omega n r. Just different parameters. So then m will be 1 over 1 minus omega over omega n squared. Sorry, this time it's going to be r, right? We are doing the whole things to make it simpler. So it will be 1 minus r squared plus 2 zeta. My pen is acting here. 2 zeta r squared. So I like to find out what is the maximum value of this m, where this m becomes max. So all I need to do, I take derivative of m with respect to r, set it to 0, lots of derivatives and stuff. So we will get to the value of r equal to 1 minus 2 zeta squared. Okay, so what was the value of r? R, we define it as omega equal to omega n. So from here, I can conclude that at omega equal to omega n, 1 minus 2 zeta squared, the amplitude is maximum. The amplitude is max. And you need to be very, very careful. I've seen it a lot in the past that the student confuse this value with omega d. Omega d is totally different things. If you remember that, we call it a natural damping natural frequency. Note, omega d is equal to omega n 1 minus zeta squared. So there is 1, 2 here. All right, these two things are totally different. Omega d is a damping natural frequency. This omega that we just found, we found the value for omega, the force that we apply, the frequency of the force that we apply, which gives us a peak of vibration, gives us a maximum number for this m. What is this m? M is the magnification factor. It gives me how much x I will get. All right, so be careful about that one. So if you look at these numbers, is this number bigger or smaller than omega n? It's obvious, right? It's smaller than omega n. It means my peak happens slightly before omega n. So I'm going to write it down here. So let's move these things somewhere out of the way. Or just delete it. So for this case, we say, so the peak of m is slightly before omega n. Right? So if you remember, in case of when no damping, omega equal to omega n gives us the resonance, right? We had resonance. But in this case, it's slightly before that. And another difference is this time it's not going to infinity, unlike zeta equal to 0. If I plot the graph, I'm going to get a graph like this one, and it's end up somewhere, and it's not going to cross this time square root of 2. So this is just for an arbitrary number. Let's say zeta equal to 0.5. Okay, and we need to pay attention that the maximum happens slightly before that. So this is where the maximum happens, and that number is not 1, is 1 minus 2 zeta squared, right? See, here we found that omega over omega n equal to square root of 1 minus 2 zeta, and 2 gives us the peak, and that's where the peak happens. Okay, I'm going to stop here and see if you have any question. Let me check chat. So the question is, if we plot omega over omega d, then the max would be at omega equal to omega d. No. Again, that's what I emphasize. Omega d is a different numbers. Omega d, again, I write it down here, is omega n square root of 1 minus zeta. This is what people get confused. They think if the resonance for a case with no damping happens at omega equal to omega n, then they say when we have damping, the resonance will happen at omega d. No, it's not. And you see the math, it's showing us that the maximum happens at omega equal to omega n, square root of 1 minus 2 zeta squared. All right? So again, do not confuse this one with omega d. When we have damping, the maximum happens a little below omega n. And what is that value? Square root of 1 minus 2 zeta squared. And what is the maximum value? If I substitute this one into m and I do the math, I will get an ugly equations, but approximately m max is equal to 1 over 2 zeta. All right? So this peak over here, we can have the exact number, but if you look at the graphs, you see when these numbers 1 minus 2 zeta squared, it's very close to omega over omega n equal to 1. And if you look at the graphs that was produced by the computer, the one at the top, this peak actually is very, very close to what we get when we are at omega equal to omega n. So this peak then is just 1 over 2 zeta. And this is the value that people use. You can substitute still that value or over there, and you will get like an extra term, which is very small, and you can substitute it and approximate it 1 over 2 zeta. And this is an important value, 1 over 2 zeta, which we need to remember that one. So in any system with damping, there is a peak of vibration that happens close to omega n, very, very close to omega n, and we need to avoid it. And that peak is 1 over 2 zeta, gives us a magnification factor of 1 over 2 zeta. Zeta is usually a very small number, so it means m is a big number, it's not a small. When you don't have damping, when zeta is equal to 0, m is infinity, and the graph is also showing it to you. In case when the damping is bigger than 1, like this one, which shows zeta is equal to 1, and then when damping is bigger than 1, we'll see there is no vibration, and this m is very, very small. Okay, let's see any question in the chat. So how did we get omega over omega n? We take the derivatives. You can try it as well. We were interested to find the maximum of this function, right? If you want to find the maximum of this function, what do? You take the derivatives, you set it equal to 0, and then you will find R. Now let me add this note here. To find the maximum, all right, to find the maximum m, this is what we will do. All right, so in order to find the maximum, what you need to do, you take the derivative of m with respect to r. What is r? This is just a new variable that I introduced to make my life easier when I take the derivatives. So I will find r. R is this value, which now we know what is r. It is omega over omega n. And what this signifies, it tells us that at this frequency, the amplitude is maximum. Why? Because dm over dr becomes 0. Okay. What is the value of the maximum? Approximately is 1 over 2 zeta. Any questions so far? Okay, I'm going to check chat. Is there an intuitive reason why the maximum occurs just under omega n? That's a good point. Why it just happened right below omega n? I've never thought of that. Always I rely on the math that telling me that it happens right before omega n. But why it happens slightly before omega n? I guess with the same reason that we prove for, like again, mathematically for why the resonance happen at omega n, right? We are resonating the system at exactly the same frequency as its natural frequency. Yeah, no, the answer to your question, good question, I don't know. Yeah, I just look at the math and it shows me that the maximum happens right before omega n. But it will get more interesting because next topic we will solve a problem that the maximum happened right after omega n. And I guess it is just math, nothing else. And also you notice that it's not a huge difference, right? It is still close to natural frequency, but maybe because of the damping, there is a slightly delay, or that's not a good term. Anyway, so maybe I'll give it some thought and I'll get back to you. But that was a tricky question. Who asked that question? I forgot. Thanks, Philip. All right. So now let's solve a more practical problem, and that is the base motion. We solved the base motion before when there was no damping, and now we added damping to the system. So again, we assume that this base has a motion of which is y, a harmonic motion, sine omega t. Okay, so this base has a harmonic motion. Again, for now, we'll just focus on harmonic motion, but soon you will be able to solve problems when this y can have any function. But now, just for understanding the concepts, to learn what's going on, we just rely on harmonic motion. So rather than a force, this time we have a displacement. For example, this y can be 10 millimeters sine omega t. And it has a meaning, right? When I have, let's say, y equal to 10 sine 100t millimeters, it means this base moves ups and down with the amplitude of 10 millimeters and frequency of 100 hertz in every seconds, how many times it repeats. So then keep in mind, this is not a displacement, this is not a force, it is a displacement. It is a displacement. That's one thing to distinguish when you solve problem. If it is a force, like the previous example that we solved, now this is a displacement. All right, so I selected a coordinate for motion of m. It is x going up, and still we are in single degree of freedom. Therefore, we assume that somehow the motion of these things is being constrained to just x motion. It means maybe there are some rail or something, and this mass does not go left and right. It just moves ups and down. The same with y. So I start by drawing the free body diagrams for this mass. Like always, it moves up by x. Then I will have the resistance force by the stiffness, and obviously the damping is opposite to the motion. So what is the force for a stiffness? All right, now we need to pay attention. I have an x here and I have a y over there. So m moves by x, but then y push it back by amount y sine omega t. So here I will have the force then, which is k x minus y. Similarly, for the damping, it is very similar to the stiffness. It is just, instead of displacement, it is a speed. So we don't care about the weight because the weight is sitting on the spring and it creates some deflection there. So we write down our equation. Sum of the force is ma, and we know our opposite direction is what we decided initially over here. We could have selected downward, then this equation would have been different, and then we'll get a different, let's say, free body diagrams, but at the end, everything will be the same. So if I write down, I would get minus k x minus y minus c x dot minus y dot is equal to m, my acceleration, which is x double dot. I order this equation, mx double dot plus cx dot plus kx. And on the other side, what I have is ky, right, plus cy dot. So I replace them by their derivatives. So I would get mx double dot cx dot plus kx is equal to ky, which is k capital Y sine omega t plus cy dot, which is c omega y cosine omega t. And this is now my differential equation. All right. So I give you a moment to see where it comes from, right? We didn't do anything unusual. We just draw the free body diagrams. We write the Newton equation, and all we did at the end, we substitute this y and y dot. So we got to this equation. So this is exactly similar to what we had before, but this time, instead of one external force, we can pretend that we have two external forces. One is sine omega t, another one is cosine omega t. One of them has the amplitude of ky, and another one has the amplitude of c omega y. All right. And luckily, we can use the superposition property. Why? Because we assume the vibrations are small, the displacements are small, and this differential equation we can solve it linearly. So we can use the superposition property. It means I can solve this equation one time, pretend that I have only ky sine omega t, and I solve it again, I pretend I have c omega y cosine omega t. I combine everything to get the final answer. But let's say that somebody did all the hard work and we just care about the final answer. xt will be x sine omega t plus phi. That's the response of the system. Let's move it back. Or some of you may try later. You can start by xt x e to power of I omega t, similar to what we did for the previous equations, and solve the whole things in one shot rather than superposition. But at the end, you will get to the same answer. This time, anyway, with each method you will use, you will get x will be equal to, or let me write it down just below it here. We save that area for the graphs. So x is a little bit uglier than the previous form. 1 minus omega over omega n squared 2 zeta omega over omega n squared. Very similar to what we had before, except on numerator we have 2 zeta omega over omega n squared. These equations, of course, for your exam, you don't need to memorize them. For future in work, if you ever need to use them, again, they are all available. But after a while, if you use them a lot, like me, you just memorize them. Again, some garbage maybe take up some place in your mind. But anyway, this is then the answer. This is the amplitude of vibration. And what about phi? Luckily, phi has the same function as before. Tangent inverse of 2 zeta omega over omega n 1 minus omega over omega n squared. Except, don't forget, this one has a negative things. Everything similar to the previous one. Right. Let me stop here and see if you have any question or if you're taking notes. And then just to recap, we have a system, a base motion. We draw the free body diagrams. We write the equation of motion. We ended up with the exact same standard equation that we had before. mx double dot cx dot plus kx is equal to something sine omega t plus something cosine omega t. We solve this differential equation. The response is xt, x sine omega t plus phi. What is x? We can find it from these equations. And what is the phase phi? Again, we can find it from these equations. Okay, so I'm going to stop and see if you have any question here. And again, if you go back and check your notes from the base motion with a case without damping and put zeta equal to 0, exactly you will get the same equations as before. So let's attempt then to quickly plot these things. x over y. I guess I forget something here. Let me double check something. So this x, now that I have a base motion, it should have a ky over here. All right, please correct it here, guys. It has a ky over here. So that's good that I remember that one. Maybe I'm really getting old. Now my memory is not as good as it used to be, like my back. So we have a ky here, guys. Ky. So because the one for the square, it or sorry, it is just y because then the unit doesn't make sense, right? So it is just y here. Now it is correct. So x is equal to y multiplied by that numbers. And we usually, the way that we write it, we write x over y is equal to square root of 1 plus 2 zeta omega over omega n, 1 minus omega n squared, 2 zeta omega n squared. Okay, now it's correct. And this value, we call it magnification factors. All right. So now this is the correct version and complete version. For x, we have equal to y multiplied by that square root. And typically we divide x by y because we care about the ratio of x over y. What is x? X is the amplitude of vibration for mass m. What is y? Is the amplitude of base motion. Let's quickly, with the time that left, attempt to plot these things. As usual, we care about a line that is around 1. Like always, we plot a case where omega over omega n is equal to 1. And this is simply m or x over y. Start with a case when zeta is equal to 0. So when zeta is equal to 0, you can see the equations become simple. At the beginning, I don't have anything. So it is 1 then, right? This value is 1, and it goes to infinity. And then when everything's go to infinity, it comes back to 1, I believe. Let's double check. We are going to have omega over omega n. Yes. Comes down to 0. Right? So remember, this is for a case when when zeta is equal to 0, m simply is 1 over 1 minus omega n squared. And this one is the square root of 2. And don't forget this m, we just care about in this scenario, just the positive, the magnitude of it. Okay, so this is for this scenario when zeta is equal to 0, previous one that we had. All right. Now we can do the same scenario, take the derivative of m and see where it happens, where the maximum happens. The maximum for this one happens slightly after 1. But I let you to take the derivatives and have some fun with it and find that value for me. Take the derivative of m with respect to r, set it equal to 0. What is r? R is the ratio of omega over omega n. And what is r? The value where the maximum happens. Okay, so this is the question we want to answer. Where max occurs. We take the derivative of m with respect to r, and your task by Wednesday is to find that value of r. Just a hint to you, it's slightly after 1. All right, so I'm gonna save these things. And yes, I'm gonna stop to see if you guys have any question. And thanks again for attending the class. And sorry for any inconvenience. Hopefully next week we will be back to the regular in-person classes. I will post also the video if you like to watch it later as well. We'll continue on Wednesday, but I'm happy to stay in the class to see if you have any answer. And so I will just respond to your question. I'm just gonna stop sharing here. And stop sharing. Okay. All right. So let me check the question on the chat.